Greetings, students. On the 5th of August 2023, Professor Penn evaluates a nice product from Ramanujan, where at some point during his video, he uses the infinite series expansion for 1 over cosine of pi x over 2 and leaves the proof or derivation for another separate video. So I decided to man up and actually derive it for you because it seemed very similar to another video that I've done before to get a nice closed form expression for family of series. And the way to actually tackle this problem is to write the Fourier sine series expansion for the function sine of tx, where t is assumed to be not an integer and x is in the interval 0 to pi, half period pi. So we're taking L, which is the half period in Fourier coefficient formula, as pi. And I'm going to write the Fourier sine series for this function. So we know that at the end of the day, our function sine of tx would look like something like this. The infinite series and running from 1 to infinity of 8n's times sine of n pi x over L, where L is pi, so we just get sine of n x, where we can find the coefficients an as 2 over pi times the integral from 0 to pi of the function sine of tx times sine of nx dx. So now I'm going to evaluate this integral. It's very simple and elementary. And when I wanted to do it, I just got the answer from the software. But here I take the time and actually solve that integral. So let me call that integral I, and I'm going to make sure that I don't forget to multiply it by 2 over pi at the end to get the correct expression for an's. And here we're going to use the product to sum formula for the product of two sine functions. The sum and difference identities for cosine are as follows. We have cosine of alpha minus beta as cos alpha, cos beta plus sine alpha, sine beta. And if I change negative beta to beta, this plus sign also changes to a minus sign. And if we subtract the bottom from the top and divide both sides by 2, on the left we get half of the quantity cosine of alpha minus beta minus cosine of alpha plus beta. We are subtracting these two, so on the right side these two cancel out and this negative sign turns into a positive sign, and we get sine of alpha, sine of beta. I'm dividing both sides by 2 already. So we can write our integrand sine tx times sine nx using this formula, taking tx as alpha, nx as beta. Sine of an x, sine of tx becomes 1 over 2 times cosine of n minus t times x minus cosine of n plus t times x. And for our integral I, we're going to evaluate this from 0 to pi. So let me copy and paste this, and we're going to evaluate this from 0 to pi. I'm going to expand these. Oh, before that, I forgot to actually integrate this. So that's not the expression we're going to evaluate at 0 and pi, I would be this integral from 0 to pi with respect to x. So we get 1 over 2 times 1 over n minus t sine of n minus tx minus 1 over n plus t sine of n plus tx evaluated from 0 to pi. Yeah, that's much better. And if I expand this using again sum and difference identities, here we get sine of nx cosine of tx minus sine of tx cosine of nx. And from the first term, sine nx times cos tx, n is an integer, definitely. And at 0 pi, we get 0. So this term zeroes out. From the second expression, we get 0 at the lower bound, and at the upper bound, we get negative sine of pi t times cosine of n pi. So we get 1 over 2 times 1 over n minus t times negative sine of pi t cosine of n pi. And for the second term, we also do something very similar. If I write the expanded form of this, again using sum and difference identities, we get sine nx cos tx, which is again 0 at 0 and pi, plus sine tx cosine x, which again gives us 0 at 0, and at pi we get sine of pi t times cosine of n pi, and there is this factor of negative 1 over n plus t. Sine of pi t cosine of n pi. Okay, perfect. Now, you all know that this cosine of n pi can be written as negative 1 to the n, and we have one extra negative sign in both of these terms. So I'm going to pull out a negative 1 to the n plus 1 along with the sine of pi t to the outside of square brackets. So we have 1 over 2 times negative 1 to the n plus 1 times sine of pi t times the quantity 1 over n minus t plus 1 over n plus t. And simply, if you combine these two, add these two fractions, we get n squared minus t squared as the common denominator. And if we add these two terms, t and negative t cancel out, and we get 2n, where these two cancels with that two. And finally, we get negative 1 to the n plus 1 times n times sine of pi t all over n squared minus t squared. Yeah, finally. And it matches the answer I got here. Negative 1 to the n plus 1 and sine of pi t over n squared minus t squared. Okay, this is our integral I, and our an's, the coefficient of sine nx in the Fourier series expansion, has an extra 2 over pi. So finally get our an's as 2 over pi multiplied by this quantity, which I'm too lazy to write it. So finally, we have the Fourier sine expansion for our function sine of tx. And I can pull that 2 over pi out, and then the series, and from 1 to infinity of these terms. And sine of x. And I think it's pretty obvious now that we're gonna set x equal to pi by 2. And there would be no problem because pi by 2 is actually within the interval that we wrote the Fourier series for, so there is no issue of like discontinuity and convergence. So setting x equal to pi by 2, we get sine of pi t over 2 equals to all of this. And I'm going to change that x to pi by 2. Now, sine of n pi by 2 is 0 at even ends. So this series would contribute only when n is an odd integer. So I'm going to change all the n's to 2k plus 1 and start k from 0. So we get sine of pi t over 2 equals 2 over pi times series. I can change that to k, it doesn't really matter, it's just a letter. But okay, k starts from 0, goes to infinity. We have negative 1 to the power of n plus 1. And if n is going to be odd, then n plus 1 is even, and negative 1 raised to an even power is just 1. Okay, so nothing there. And this n changes to 2k plus 1. And we have that sine of pi t. And by the way, that's a constant with respect to the series, so I'm also going to pull that out. Okay, perfect. And then in the denominator, we have n squared minus t squared, which changes to 2k plus 1 squared minus t squared. And we also get sine of 2k plus 1 pi over 2. Okay, sine of 2k plus 1 pi over 2. We can write it as sine of k pi plus pi over 2. And it gives us sine of k pi cosine of pi over 2, which is 0, plus cosine of k pi sine of pi over 2, where sine of pi over 2 is 1. And we just get cosine of k pi, which is negative 1 to the k. And since that's quite easy and probably most of you know, have came across this just evaluates to negative 1 to the k. Okay. So now we have sine of pi t over 2 equals to 2 over pi times sine of pi t times the series k running from 0 to infinity of negative 1 to the k times 2k plus 1 over 2k plus 1 squared minus t squared. And the obvious step here is that I'm going to divide both sides by sine of pi t. And also I'm going to use the double angle formula for sine alpha, where we can write sine of alpha as 2 sine of alpha half cosine of alpha half. So on the left side we have sine of pi t over 2 divided by 2 sine of pi t over 2 cosine of pi t over 2. And you notice that sine of pi t over 2 is cancelled out, and what we expect nicely emerges. Okay, And on the right, you have 2 over pi multiplied by this infinite series. And the only step left to reach our goal is to multiply both sides by 2, and on the left we only get 1 over cosine of pi t over 2. And we're actually done. On the right we get 4 over pi times that infinite series. And the only thing you need to make this result look exactly like this thing here is to change k to n and change t to x, and that's what we get at the end of the day. And as Professor Penn says, I also think this is a good place to stop. Thank you.